This is the Introduction to Time series, the last module in this year's series. So the whys and the whats, time series. So far we've looked at cross-sectional data, or data with one time period but spanning multiple units. So people or school districts or states. When we've been looking at the test scores versus student-teacher ratios, we've been thinking about schools, which are which is a cross-section. We have many observations of school districts with only one time period. Time series is the opposite. It's the evaluation of one entity over time. So we might only have one school district we're looking at, but we have many observations of that school district over time. Another example is, how does one person's health change over time? Or how did traffic fatalities in Colorado change after marijuana was legalized? The unit of analysis is traffic fatalities in Colorado. And we have a time series of it. We have it over time. Time series is useful for looking at dynamic causal effects, or the effect of legalization on traffic fatalities in Colorado this year and next year and the year after and so forth. And it's useful for forecasting. What is the best forecast of next month's unemployment rate, interest rates, stock prices, or commodity prices? A key difference in time series analysis. So far we have been concerned about the causal effect of X on Y. When we write down our model, such as this, we have been thinking about, get rid of that for a sec, been thinking about the causal effect of X on Y. Beta 1, we're looking for an unbiased estimate of beta 1, right? In time series, we aren't always concerned about causal effects. If we are interested in forecasting, we don't need to identify causal relationships. So, for example, if you see people walking down the street with umbrellas, you can use that to forecast that it is going to rain. Right? Even if you don't look at your weather app on your phone, if everyone outside has an umbrella, you can think that all those people know something that you don't about the weather. They might think that it's going to rain. But people carrying umbrellas does not cause it to rain. So this is the difference between causal relationships and correlation and forecasting. The notation, suppose we were trying to forecast GDP. Let Y equal GDP. I should note that in the previous slide, when we were looking at beta 1, the implementation of regression doesn't change if we think of it as causal versus correlational. We still get estimates of beta 1. It's just the interpretation of the coefficient that's changing. So, okay, back to this slide. YT equals GDP in time period T, where T can be days, weeks, quarters, years, decades, etc. If T is quarters, so we're measuring GDP in quarters, the first lagged value, or T minus 1, is GDP last quarter. The second lagged value, T minus 2, so T is this period. So in this case, let's make this really concrete. So T is, let's think if we're doing this in years, T is 2021, and T minus 1 equals 2020, T minus 2 equals 2019. The first lead value, so we can have lags and we can have leads, the first lead value, T plus 1, is GDP next quarter. So remember, we're thinking of quarters. The first difference is today's minus yesterday's, or this quarter minus last quarter, or this year minus last year. And we write the difference as this triangle. The first difference of the logarithm, the change in the log of yt, is the log yt minus the log of yt minus 1, which gives us approximately a % change in y. An example table. So here we have 3 quarters. We have GDP in each quarter, and then we have the log GDP in each quarter. And then we have the annual growth rate, which is equal to 400 times x, where x is going to be the values of the log GDP, 400 times the change in the log GDP. So the change in the log GDP is just going to be the difference in each of these subsequent values here. So we would have, for example, 9.645 4 for t equals 2 minus 9.641 for t equals 1. And so this would be the change in log GDP. And since we're dealing with quarters, we have to multiply it by 4, and in this case 400, to get to an annual growth rate. And so these changes are then going to be 3.64%. So we're multiplying by 4 because we're doing quarters, and 100 because we're trying to get to percentages. So 3.64%, 1.2%, and 2.75% are the changes in the growth rate over time. The first lag growth rate is 4.75. Doesn't show up on here, but that would be quarter 0. If we had it written down up here in our table, we would have 4.75. Or actually, sorry, it should be not there. It would be here, 4.75. The second, the lag growth rate for period 2, it's just going to be 3.64. So we're taking these values and moving them up like this. So the first lag growth rate is going to be, if the annual growth rate is written as, let's write it as y t, the first lag growth rate, what we're talking about in the last column, is yt minus 1. Autocorrelation. Serial correlation and autocovariance. So autocorrelation is the same as serial correlation, and now we'll introduce what these are. In time series, the value of y in one period is typically correlated with the value of y in the next period. Autocorrelation is the correlation of a series with its own lagged value. So the first autocorrelation is the correlation of yt, current period y, and last period t minus 1. The second autocorrelation is the correlation between current period y and the y in 2 periods ago. And we can do this to the jth autocorrelation, so it's just going to be t minus j here. The jth population autocovariance and autocorrelations can be estimated via the sample covariances and correlations. So the first autocorrelation, or the autocovariance here, is just going to be the covariance formula, which is yt minus its mean for all y's time periods of j plus 1 to the t. So t, we're summing from t equals j plus 1, and then yt minus j, so the previous periods t minus the mean for all in the previous period. So in practice, this is going to be like yt, or y1 minus y1 y1 plus 1 all the way up to the t. So the mean over all y values less than t. So this is just a covariance formula. So if we can think of each of the yt's as being independent random variables. So this is essentially y minus its mean, and this is x minus its mean. That's another way of thinking about it. And then we're doing the average of those, and that's just the covariance formula. And this gets us the average. And then to get the covariance, the correlation, sorry, we normalize it by dividing by the variance of yt. The first 4 sample autocorrelations of the growth rate in the previous table of GDPs are 0.34, 0.27, 0.13, and 0.14, which suggests that GDP growth rates are mildly positively correlated. In other words, if GDP grows fast in one period, it will tend to grow fast in the next period. Time series can have completely different looks. So here we are plotting different time series. Here's the U.S. unemployment rate. You can see it has this nice sort of cyclical pattern. The dollars per pound, we get these discrete jumps. And so if you're doing time series analyses, you have to think about all of these things. You have to make sure you're controlling for discrete jumps and for the trends in the time series, and here we have unemployment rates with a clear trend, and then here we have an exchange rate that just looks like a bunch of random noise. So we can have unemployment rates, different sort of structures to our time series. The unemployment rate has relatively smooth swings. The dollars per pound has what we talked about, structural breaks. Number C, or letter C, is the logarithm of unemployment rates. This grows fairly constantly but levels off, and then D is essentially like a stock price which fluctuates widely. We have to think about dealing with all of those things in time series.